In this video, we're going to take a slightly more formal approach to greedy algorithms. We want to know the 3 steps to designing a greedy algorithm. The first step is we want to design the algorithm so that after we make a choice, we are left with a single subproblem to solve. Now in dynamic programming, we're not so concerned with that. We can have multiple subproblems that we call recursively. In greedy, we only want one. We need to prove that the optimal solution has the greedy choice in it. In the activity selection, optimal activity selection problem, we showed that given an optimal solution, we could plug in the greedy choice, which was the activity with the shortest finish time, not the shortest finish time, but that was going to finish first. We plugged that into the optimal solution and found that this new solution was identical to the optimal solution. Then we want to prove optimal substructure. That is, the optimal solution, which is equal to the greedy choice plus the optimal solution to the subproblem. So that's our optimal solution, but we also want to show that this right here is true, that the subproblem solution, that is the optimal solution to the subproblem, and that is a member of the global optimal solution. Let's explore a little bit more greedy versus dynamic. Now notice they both require optimal substructure. Now let's explore the difference between them using an example. The example of the knapsack problem. The problem is this: a thief goes into a store, and there are n items the thief can take. Now each item has a value. So v sub I is the value of item I. Each item also has a weight. And the thief wants to take the items, the most valuable hoard he can, without exceeding a total weight. Now there are 2 forms of this problem. We have the 0-1 problem, which is we can either take an item or not. So yeah, maybe the items are gold bars and silver bars and copper bars, and so we either take a bar or we don't. This requires dynamic programming. But there's also a version called the fractional version. And here we can take part of an item. So in this case, we might have a pile of gold dust, and a pile of silver dust, and a pile of copper dust. And so I can take the entire pile or part of the pile. And it turns out, interestingly enough, that this can be solved in a greedy manner. But both have optimal substructure. So let's look at that. Here I have my sack. And I have some items. Here's my sack. If I remove item I, then what's left here is the optimal solution for weight W minus W sub I. So that is optimal substructure. Okay, so let's explore the fractional algorithm first. This is greedy. The way we're going to solve it is we're going to compute the value per pound. Which is going to be the value of an item divided by the weight of the item. We'll fill the sack with the item with the most value per pound. And when that runs out, we go to the next item of next value. Okay, so that's the fractional, and then we have the 0, 1, and this is going to be solved with dynamic programming. Now let's bring up a figure from the book. This is on page 427. Okay, if we look in figure A, we have 3 items, and our knapsack can handle 50 pounds. So what are our options for the 0, 1 problem? We have 3 options here in B. We can put in the 20 weight item, item 2, and then item 3. We could put in item 1, then item 2. We could put in item 1, then item 3. Now, a greedy approach, the greedy approach we use in the fractional algorithm would say we want to use the item with the most value. So this is 60 over 1, which is a value of 60. This is $100 over weight 2, which is a value of 50, or a value per pound. And then this is the third item is $120 over 30, which is equal to $40 per pound. And so we would want to fill up using first the 10 weight item 1, and then item 2. So this is the greedy solution right here. But notice the total value here is $160, while the value here is $220. And you can kind of see why. Here we've got so much space left over that we could have used with something of lesser value per pound, but it fills up the knapsack more. And so for this, we're going to have to use a dynamic programming approach. On part C, however, we can use a greedy algorithm because we can always fill up the space. So we use highest value, next highest value, and the next highest value. And we get something that's actually more valuable than the 0-1 approach. So that's an example of a problem with a very subtle difference that's going to cause us to require to use dynamic programming versus greedy.